This is the last lecture in Unit 4, and it's on transformers. So we're now going to look again at the interaction between electricity and magnetism. So you might have seen a device like this. This is a charger for a phone or some other device. It actually transforms the energy or the voltage from your wall outlet from 120 volts to a lower voltage that's needed for electronics, like 12 volts or lower. These devices are transformers. Anything that changes a voltage to a lower or a higher voltage is called a transformer. So it's a device that changes, that raises or lowers a voltage. They use the concept of Faraday's iron ring. Now, in Faraday's iron ring, the number of coils around the primary and the secondary were equal. But what was determined was if we make the number of coils different, we'll have different voltages and currents on each side of this circuit. So it's not necessary to turn the switch on and off to produce a current in the secondary circuit. All we need is a varying magnetic field in the ring, which means we need a varying or alternating current. So if we use alternating current, we will have an alternating magnetic field. So this will always be on. If we have it as DC, then it only happens when we're inducing or we're magnetizing or demagnetizing that soft iron ring. Transformers have no moving parts. This is because they use AC current, and according to Lenz's law, the alternating current in the primary circuit produces a varying magnetic field on the ring, which passes through the secondary circuit and produces an alternating current in the secondary circuit. How does Faraday's iron ring help the manufacturer who needs a different voltage for a device? Transformers have different numbers of windings in the primary compared to the secondary circuit, so that's how they work. So let's look at a step-down transformer. This is one where we have more windings on the primary side and less windings on the secondary side. So a step-down transformer, it decreases the voltage in the secondary coil. Then we have a step-up transformer. This is where we have more windings on the secondary coil and less on the primary side. This increases the voltage in your secondary coil. And transformers are defined based on how they increase or decrease voltage. So we step up the voltage, we step down the voltage. That's how we define it. Not based on current, but we'll get into that as well. So equations for transformers, because the energy in the primary has to equal the energy in our secondary, and energy is equal to power times time, and power is equal to V times I, we can say that our V times our I on the primary has to equal our V times our I on the secondary. We can also note that the ratio of the primary voltage to the secondary voltage is equal to the ratio of the number of windings on the primary to the number of windings on the secondary. So we can come up with this triple equation for transformers. Vp over Vs equals Is over Ip equals Np over Ns. Notice that I is switched. Suppose you increase the number of windings on the secondary coil compared to the primary coil. What would you expect the effect on the voltage and current to be? So voltage increases in a step-up transformer, but current decreases. This is because the conservation of energy states energy on the primary has to equal to energy on the secondary, and because energy is power times time, and because the time is the same, that we just compare the power. Power is voltage times current. So if we increase the V, the I must decrease in order to have the same value for energy. Number 3, this one says we have a door chime designed to operate at 8 volts connected to a 120 volt power supply through a transformer. In the secondary coil, the number of windings is 100 and the current is 1.8. So let's solve this here. First, let's start with our equation, Vp over Vs equals, get that to resolve, Np over Ns. And we need to solve for primary coil, so we need to solve for Np. So that's Ns equals Vp over Vs. So Np equals 100. 120 is our primary, and 8 is our secondary. So turning on our calculator here, 100 times, oops, not showing up, 100 times 120 divided by 8, we have the primary coils being 1,500 windings. What's the current in the primary coil? So our current would be, let's go back to Vp over Vs equals Is over Ip. So Ip in the primary would be Is Vs over Vp after rearranging. So Is is 1.8. Here we have 8 over 120. So this is going to be smaller. Let me turn on the camera for the calculator here. 1.8 times 8 divided by 120. We're left with 0.12. So those are our two solutions. So what type of transformer is this? Well, it's going from 120 volts, because that's the connected side, the primary, to 8 volts. That means that it's a step down. It's stepping down the voltage. Question 4, we have a transformer with 60 windings in the primary coil, and we have 300 windings in the secondary. We're supplying a compressor motor requiring 2 amps and a potential difference of 550. So what are the current and the potential differences in the primary coil? So we know the voltage, we know the current, or we know the secondary values. We also know the number of windings. So the Np over the Ns equals, let's do the current first. So that would be Is over Ip. And I need to find the primary. So Ip equals Is Ns over Np. Is is 2.0. Ns is 300 over 60. Two times 300 divided by 60. We have 10 amps. Same thing, but now we're using voltage, which means we have a Vp over a Vs. We have to solve for the Vp, which is Vs Np over Ns. So Vs is, I have to move the calculator because I can't see the question, 550. Np is 60 over 300. So let's check the calculator here. 550 times 60 divided by 300. We have a voltage of 110. So those are our two questions there, solved. A student is discussing transformers and states that the voltage and current both increase in a step-up transformer. That can't happen because of the law of conservation of energy. Power in has to equal power out. So if the V increases, the I has to decrease. If AC and DC generators are equally easy to design and operate, why is the AC generator the only one used for large-scale electricity? So because of power loss, and it's defined by I squared times R, we need to reduce the current and have a high voltage, have a high potential difference in order to not lose as much energy. Because the higher current we have, the more chance we have for energy to transform into other forms. And because we want to avoid that, it's better to have a higher voltage, which is how much energy we have per unit charge, than have a lot of charges flowing through. That's why we have a power generation system with very high voltages, up to 500 kilovolts or higher. So for the energy generation distribution system, we use AC for large-scale energy production, and there's a series of step-up and step-down transformers that are used to distribute the energy. You don't need to know the exact numbers, but they start at very high values in the high kilovolts, and they end up at 120 or 240 volts at your household. So let's look at power loss. Here's a question. It says determine the power loss in each of the following. So if we were running if we had 200 megawatts of power coming from a power plant and the energy was delivered with 2 kiloamps in a 10 ohm wire, what would be the power loss in that case? So we would have our power loss is determined by the I squared R value. So and you could calculate power in a number of different ways using voltage as well, but if we're transporting the energy using a high current, we would use this power loss equation. This would be 2000 squared times 10. And that would be 4,000. Sorry, let me just do this quickly here. I'm going to try to do it in my head, but I think it's better if I just do it this way. So 2,000 squared, so multiplied by 2,000 times 10. So that is a 40 megawatt power loss. And if we wanted to compare that as a percentage, 40 over 200 is a 20% power loss. Let's look at question 2 here, or part B. It says determine the power loss in this situation. If we have a 200 amp wire, or sorry, 10 ohm wire and a 200 amp current. In this case, I guess I won't calculate it again, I'll just show you the calculation. So if we have 200 amps, it's only a 0.2% power loss. So it's more beneficial to have a lower current. What if we have a 3,000, with the calculator out of the way, 3,000 amp and a 0.5 ohm wire? So we reduce the ohms, 3,000 times 0.5, it's 45% power loss, so still pretty significant. So you want to reduce the current flow. The current flow is squared in your power loss equation, so you want to reduce that in order to have the most amount of energy delivered.